I'd like to show this picture so that you know what each of the Play-Doh pieces represent throughout the project. Now let's begin. The resting membrane potential is when a neuron is not transmitting an impulse, like seen here. It is important to notate that in this state there is more sodium on the outside and potassium on the inside. At resting potential, the charge on the inside of the plasma membrane is -70, and the charge on the outside is +30, making it polarized. When a neuron is transmitting an impulse, it is called action potential. The rapid sequence of depolarization and repolarization takes about 1/100th of a second. As the action potential travels along the body of an axon, if threshold is reached, it triggers the voltage-gated sodium ion channels to open, causing an influx of sodium ions into the plasma membrane. This, in return, causes an efflux of sodium ions on the outside of the membrane. Because of this, it causes a reversal of charges on the inside and outside, and it becomes more negatively charged on the outside and positively charged on the inside. This sequence of events is called depolarization. The impulse moves down the axon. Because the charge on the inside of the plasma membrane is +30 millivolts, gated sodium channels close and gated potassium channels open. This causes an influx of potassium ions to rush outside of the plasma membrane. This process is known as repolarization. This reversal causes the charge on the inside of the plasma membrane to start going back to -70 millivolts. While the charge may be going back, the ions are still not back in their original place. To fix that, we need the sodium-potassium pump. During this time, another impulse cannot be propagated because the neuron is in a refractory period. The sodium-potassium pump returns ions back to their original place, but because it goes against the concentration gradient, it requires ATP. For every 3 sodium that are pumped out, 2 of the potassium are pumped back in. This process will continue until all the ions are back in their original place, ready for the next impulse to be propagated. As you can see, now both the voltage and the ion concentrations on the inside and the outside of the plasma membrane are back in their original state, also known once again as resting potential. I also wanted to take the time to look at the action potential in a different form, in a graph form, so you can see the actual voltage change as action potential occurs. It is important to notate that these types of channels are measured in millivolts. Okay, so the line I'm drawing right now is threshold. That's the minimum amount of the voltage required in order for the propagation to begin. And the one right below it is -70 millivolts for the resting potential. As you can see, the resting potential is drawn as a flat line because there is no impulse that is trying to be sent. The circle I just drew indicates threshold. Since action potential is an all or nothing response, if this isn't reached, an impulse cannot be conducted. The arrow represents gradual depolarization, and above it, rapid depolarization. Both of these indicates the voltage-gated sodium channels have opened and sodium is rushing in. When the charge on the inside of the plasma membrane reaches +30 millivolts, the sodium-gated channels close, and the voltage-gated potassium channels open, and potassium rushes in. This is known as repolarization. When too many potassium ions go back into the membrane, the inside becomes even more negative, also known as hyperpolarization. To return the ion concentrations back to normal, the sodium-potassium pump kicks in, using ATP, and pumps 3 sodiums back out of the membrane for every 2 potassium ions that come back in. Hyperpolarization and the sodium-potassium pump are in the refractory period, and after, resting potential is restored.